we're at the point where we're trying to decide how many factors or components to extract from these data. And we had talked about using parallel analysis, and we had said that that was a better option than things like eigenvalue greater than 1, the Kaiser rule. And this parallel analysis, when we ran it, remember we talked about how to compare each individual eigenvalue to a randomly generated eigenvalue. But then as Casey and others pointed out, it seemed like we weren't getting randomly generated eigenvalues. And that was true. So in this graph here, parallel analysis graph that Austin just ran, it gives us a better idea of what's happening behind the scenes in PA. So the blue line, if you'll notice, the blue line is for random EV, which is random eigenvalue. And that line is very, very, yes, that line is very gently sloping, but always near 1. Those are the actual eigenvalues generated from the random data set. Then we have 2 other lines that are very closely following each other. The red line, which is our unadjusted eigenvalues, those are the actual eigenvalues we got in our analysis. And the black line is the adjusted eigenvalue, and it's adjusted for basically a little bit of noise in the data. And so it adjusts for the random fluctuations that can happen if you had tested 2,000 other kids with these same measures. So every time our blue line is below either the red line or the black line, parallel analysis uses the black line, then we say that we should retain that component. So that very first one, both the red and the black, are up near the 4.5 to 5 mark. And that's way above the second point, the blue point, which is really just barely above 1. So we definitely retain that first component. We go to the second one and we see that it's still above the line. The third one is still above the line. The fourth one, the red one, is above the blue line. The black one is basically on the blue line. So based on parallel analysis, we're really, really close. And if you look at the output from when we ran the Paran argument, it told us 4. It basically said that in the end, we had 4 components that we should retain. And that's because that black line is still slightly above the blue dot at the 4th eigenvalue. But by the time we get to the 5th eigenvalue, you can see that the red and the black lines have actually dipped below. And so at that point, they also turn white. The dots went from black to white, which is another way of telling you that then you should not keep those components. Does that make sense to everybody?
And then one thing I wanted to point out, if you remove this all equals true argument, run it, whereas before, when our output looked like this, that it gave us each of those true. Once it runs, you'll notice that it only gives you the output for those 4. So we initially included that all equals true so that we could see all of those values, but if you leave that out, then it basically uses this Kaiser rule on the adjusted eigenvalues to let you know, hey, there's 4 that are above the random eigenvalue line. Does that make sense?
And I really like the all equals true as we're learning this, along with the graph of the parallel analysis, so you can see what it's basically doing. Parallel analysis is a little bit like the Kaiser rule, but adjusting for random noise in your data.
All right, and what I'm gonna do is I'm gonna copy and paste just everything I have in my script list for things you need, because I don't want to worry too much about going back and looking back over all the stuff that we've done. I just want to pick up right where we left off on number 10. If y'all recall, we were looking at, we exported that CSV, and we were going through all of those unrotated eigenvalues, and we were highlighting based on things that were greater than 3 and such. And instead of pulling that back up, I want to show y'all the next function, and so that we can go back and look over number 10 again, but in a slightly different way. Instead of looking through the CSV, there's a function called print psych. And so if we print psych, we're going to print our PCA none 4. So that unrotated 4 component PCA, we're going to enter in an argument called cut, and we're going to set that equal to 0.32. And all that does is in that matrix, 0.32 that we're looking for will be suppressed, so it'll come up blank. And then I'll also just tell it digits equals 3 just to round it. So now when we look at this right here looks exactly PC1, PC2, PC3, PC4. These would look exactly the same as that CSV that except for are left blank. So by using that cutoff, it can help us look a little more clearly, because if you recall, when we're looking for complexly loaded variables, that means that it's above 0.32 on more than one component. So for instance, we can look right here and see Discrim 101 is Discrim 102 is only above it on 1, so it's simply loaded. This one would be complexly loaded. These two are complexly loaded. So just entering that cut equals 0.32 is just suppresses all of the values and doesn't show them if they're less than that cutoff point. Anna, do you want to, before we go into number 11, looking at the rotated, is there anything that you want to hit on in this unrotated version?
The first thing I want to ask you guys is, what do you think these components are? Like, let's take a look at the first component. What would you call it?
Self-esteem or something.
So we have a vote for self-esteem or something. Why do you say or something?
There are those buttons in there too.
Yeah, the whole thing is a little bit of a hot mess, right? If you had to try to interpret it right now, it would be very difficult for you to say exactly what each thing is. And that's kind of the point. The point is this is unrotated, and it makes it very hard to interpret. And so we want to be sure that we looked at this first so that you had a sense of why we go through and actually rotate our components. First by trying to interpret an unrotated, and now we're going to do it with a rotation. We're going to again look at the loading matrix, excuse me, and then see if it makes more sense to us.
All right, so then when we get down to number 11, if we, let's just copy and paste this code up from number 10, because we're going to write another CSV, and we're going to go through this one also in the CSV form, but then we're just going to change the have up here where we created the or did we PCA none? Did we actually run the? We did PCA OB4. So we're going to look at this rotated one where we did the Obelman rotation up on number 8. We did is the same thing as the PCA none 4, except for instead of no rotation, we did rotation. And so if you run this rotated matrix. And now in your working directory, you should have a rotated matrix.csv. Let me get that pulled up. And it should look something like this. And compare that to the unrotated matrix. All right, so over here on the right, I have the unrotated one that we ran last week, and over here on the left, I have the rotated one. Before we get into anything else, I want to point out, notice at the top here, last week, PC2, PC3, PC4. Over here, it's numbered PC1, or excuse me, TC, not PC, TC1, TC3, TC4, TC2. The reason for that, first of all, like the PC versus TC, that's formed, whereas this is just the straight principal components. And then it retains, it can order things differently. Later on, why they don't just rename these things. There is a reason, but it's not terribly important. I just wanted to make sure to point out that they still variance. In other words, this TC1 explains the most variance, TC3 explains the second most variance, TC4 explains the third most, etc. So now that we're looking at our rotated, we're looking for first, how many have, well, I guess first highlighting all of the ones that the absolute value is greater than 0.32. So here for TC1, if we're looking, we've got this set here, SE101 through SE107, and that looks like it. So we'll highlight those. For TC3, we've got, looks like just DEP 101 through DEP 104. If I'm missing something, somebody yell at me. For TC4, looking at 3.2, we've got one right here, one right here.
In the Discrim 104, right?
Yep. And then over here, we've got these three, that one, that one.
That's it.
All right. So now looking across these, how many of these variables have complex loadings?
3.
Yep. We
So what are they?
got the Scrim 104
3.
here, SE 103. How many of these variables don't load on any of the components?
Oh, wait.
Oh,
How-
sorry. I just missed that one.
Oops.
Yep. So the correct answer here is that none of these fail to load on one of the components at least. And so then the homework asks to ask which variable loads the highest on each of these 4 components. Loading variable on TC1.
SE 102.
3.
Depth 104.
Yep. TC4.
Discrim 101.
Excellent. And so if we compare these the loadings from our new rotated matrix to those of the unrotated matrix, how do these loadings compare?
They're less complex. I think if I remember correctly, in number 10 there were like 11 or something, not 3, maybe less than 11, but there were a lot more complex loadings.
There were a lot more complex loadings.
Yeah, there were also when somebody's got bad echo. But then when we look at the actual eigenvalues themselves, like if we compare SE, right, there we go. So all of these eigenvalues have higher loadings than the unrotated matrix. I'm gonna dip away from the CSVs for a moment and come back here. And once again, I'm gonna copy and paste this PSYC. Oops.
Wait, so are these components that have the highest loadings, are they the marker loadings or the marker component?
That's what we were just about to get into.
Oh, okay. I'll wait.
For looking for these marker variables, PSYC, if you recall, for a marker variable, that is a correlation over 0.6. So instead of setting your cut to 0.32, you could set your cut to 0.6. And now when you look at your output, here you have your marker variables on, sorry, no, I need to change that back to PCOB4. There we go. So now our output suppresses any eigenvalues, any loadings that are lower than 0.6. So it makes it a little more clear to see TC2 has 2, and TC4 has these 3 down here, and TC3 has these 4 down here. If you're wanting to look at equal to 0.32, and then here you be able to look across quickly and say, okay, Discrim 104 loads onto, SE 103 loads onto, SE 105 loads onto, and you can see that you have 3. So this PSYC is just a nice way of being able to summarize that, and by changing that cut, you can make it easier to quickly identify those complex loadings and the marker variables. So then, so for this part, let me pull up our data dictionary from this, because we'll need to look and see. So the homework asks, after identifying the number of variables per component, and think about what you might name each of these 4 components. So if we're looking now at here, so if we have SE 101 through SE 107, over here in our data dictionary, through 110 don't. So you can't just call this self-esteem, because there's, well, there's 2 self-esteem things. So more specifically, looking across, sorry, SE 101 through 107 versus 108 through 110 for TC1 and TC4, what might you label these components?
I'm not quite sure what to name that part, but the second group of SEs, I think I would name worthlessness.
So we've got self-worth, worthlessness, so we can see that, like, if SE 108 through 110 are I wish I had more, and at times I think I'm no good at all, then it seems worthlessness or some sort of negative self-worth, negative along those lines, will work. Whereas on these other ones, they're generally positive things. I'd have a positive attitude towards myself. I do things as well as other people, and I feel like I have a number of good qualities. So when we look at these, this TC1 might best be named, like positive self-esteem or self-esteem. And TC4 then is going to be, you could use, worthlessness, negative self-esteem, something along those lines. Then for the TC2, it's all our discrim items, so that seems pretty clear what that component is going to be. You would name that something along the lines of, if the items are the racial discrimination, there is racial discrimination in economic opportunities in the U.S., the American way of life weakens the family, etc. It's something along the lines of, discrimination perceptions. It's how you perceive discrimination in the U.S. And then the last one is those DEP items, and so that one's pretty straightforward. You could just call that one depression or some such. Do we have any questions before we move on from there? And Anna's asking how the ease of interpretation between the rotated and unrotated matrices. So some of the people pointing out that it's an art form to just kind of pick the names that fit better. A lot of people indicating rotated matrices are easier to interpret, and that's certainly true. That's exactly why we rotate. This unrotated is kind of a mess to try to make sense of. We have our rotated matrix is going to have higher loadings. It's going to have fewer complexly loaded variables. So in general, that's why we do these rotations. All right, so moving along, we get down to number 12, and it asks us to report the correlations between our components. So coming back into R here. I'm pretty sure we already did this as well with the previous thing, but all we're going to use here is the lower mat, which was that function that pulls the lower matrix from our correlation, because if you recall, PCA OB $ R dot scores is those correlation scores from our PCA. And then the lower mat just gives us the bottom triangle, plus allows you to say digits equals 3 to round it off for us down here. Now, again, I want to point out one thing that'll be important to keep in mind as you're filling out your homework is that this will not necessarily keep things in C1, C2, C3, C4 order. So if you just copy and paste these numbers and their exact locations into the homework, it's not going to work because the homework is 1, 2, 3, 4. So where you need to enter in the correlation between TC1 and TC2, you have to grab it from down here, not from up here. So just make sure that you're mindful of the order of all of these things. So given these correlations here between our components, what might you say about the rotations, the appropriateness of using that orthogonal rotation instead of the oblique rotation?
To me, it seems like you probably could do an orthogonal rotation. They're not super correlated, but I'm not sure what the exact cutoff is. I can't remember. Maybe my notes.
Yeah, definitely on the right path there. So that cutoff, because the correlations are less than 0.3 in general, orthogonal rotations are going to be appropriate here. Technically this one is 0.302, but meh. So with these low correlations, that tells us that we can use those orthogonal rotations without problem. And as Anna pointed out here in the chat, some people use 0.32 as the cutoff. It's really more or less, well, I was going to say arbitrary, arbitrary as far as 0.3 versus 0.32, etc. Would be arbitrary. Keep in mind that this is innately an exploratory analysis. So there are no hard and fast rules. This is one of the reasons that it's important to just be transparent about the things that you're doing as you're conducting these analyses. For our weights matrix, let's go ahead and pull it up and then we'll talk about what it is. So all we're doing here is if we pull up PCA OB4 and throw in a $sign and then weights, this will give us our weights matrix. Now, this weights matrix, if you recall, it can be seen kind of like the coefficients output of a regression. So if we were to calculate 4 scores for each participant, they'll have 1 score for component 1, 1 score for component 3, 1 score for component 4, 1 score for component 2. The way we compute those scores is based on this weights matrix. You'll take whatever score they have for Discrim 102, multiply that by -0.036, plus whatever they had for Discrim 102 times -0.03, plus Discrim 103 times 0.01, plus. So just the same way that when we look at our output of a linear regression, and you can say, oh, well, or rather when you're looking at the linear formula where you say, x1 times this coefficient plus x2 times this coefficient plus x3 times this coefficient. So each column here just tells you what you multiply each of these variables by, and then sum them all up to get your component score for TC1, or for principal component number 1. So if that's the case, if we have, we'll look at SE 101 here. And if we're looking at this first component, how much is a 1 unit increase in SE 101 going to change their component score? I'm trying to find my chat box here. All right, Josh says 0.28. 0.28, yeah, there we go. So that's all this weights matrix is telling you. What's up, Josh?
Hey, for 12B, did we not use a oblique rotation to get those R scores?
Yeah, Josh, let me answer. This is weird because I'm hearing myself in echo. Are you guys hearing that too?
Nope.
Oh, thank goodness. Okay. So the reason we're doing it that way is because we need to first run an oblique rotation in order to obtain the correlations among the different components. If we had run an orthogonal rotation, we would have forced the components to be correlated at 0. And that means we couldn't have evaluated whether orthogonal was proper. That's why it's always a good idea to start with an oblique rotation, look at the component correlations, and then decide if you must keep it oblique or if you're allowed to go to force it to be orthogonal.
All right. Are there any other questions before we move on to number 14? And I want y'all to go ahead and take a shot at number 14 on your own. We're just repeating this PCA, but now we're going to do a Varimax orthogonal rotation. So we'll call this one PCA.Vmax4. And then pretty simple. It should consist of copying and pasting and changing one thing. So all we're doing here is we're changing our rotation to Varimax. Varimax has to have a capital V in this particular one. And we've now stored that as PCA Vmax 4. So we have PCA None 4, PCA OB 4, and PCA Vmax 4.
Austin, there's a question in the chat from Rosalie.
Yeah. So is that for getting the if you're talking about the component score coefficient matrix, yeah, so that's just this PCA OB4 $ weights. It's the weights matrix that is in the PCA object.
What does the loading required namespace GPA rotation mean? Because I thought you were calling this, or Anna's calling the PSYC package, and
Yeah,
the little bit of
the principal function is in the PSYC package, but the like we've said before, there are literally like dozens and dozens and dozens of different rotations. The Varimax rotation is part of a package that's called GPA rotation, and this has just a ton of different rotations. So all that's saying is that under the hood, when you run this and put in Varimax, it calls GPA rotation. It calls that library so that it can pull the Varimax rotation from it.
So when you're choosing Varimax rotation, like how did you know that that one was going to be an orthogonal rotation? Like why isn't it called something like orthogonal and not something stupid like Varimax?
Well, because there are a lot of different rotations that are orthogonal rotations. Varimax is just one type of orthogonal rotation, just like Obleman is one type of sorry. All right. Yes. So does that answer your question though, as far as?
Yeah, definitely.
Okay, cool. Yeah, like Anna says, we're not getting into all the different types of rotations. Like if you're doing a PCA or an EFA for something, then it might be good to look into some articles that describe some of the nuance between different things and see what's most appropriate for you. Really, the main thing that we're focused on is orthogonal rotations versus no rotation, and so then here on number,
I think that's the other one, oblique.
Oblique. Yeah, I haven't had nearly enough coffee this morning. So now that we've done this Varimax rotation, you can take a wild guess at what we're going to do next for looking at how many complex loadings there are. Once again, it's copying and pasting from before. If you recall, at the very beginning of all this, we told you that there's only a few new things that we have to do, and then it's just going to be repeating those things with different things over and over and over. So now we're going to do our print psych, just copied and pasted from above, but change it to Vmax 4. And I'm going to go ahead and leave that cut at 0.32 so that we can look at our complex loadings. And then how many complexly loaded variables do we have? Yep, got a lot of 4s popping up, and that's what I'm seeing from my end. How does that compare with our last one? Yep, just one more complexly loaded. So then for the next part, which variables load highest on these? And notice on this one, it's called RC instead of TC or PC. So when it was that original unrotated, it was labeled PC1 through PC4 for principal component. When we did the oblique, it was TC1 through TC4, where it was the transformed. RC1 through RC4, it's the rotated component. So don't get too wrapped up in, like, just focus on the C part, C1 through C4, that it's the component. If you were doing this in SPSS, it would just call everything, you know, the principal components. So don't get too hung up on that. But what is the highest loading component, or the highest loading variable on component 1?
SC 102, loading at 0.757.
And the next one, RC4.
SC 109.
Good.
33.
Yep. Component 3.
Dep 101. Oh no. Yeah, 101.
And
no, what? Whoops.
Yeah, Dep 104. And then for the last one, we got the Scrim 101, as I'm seeing pop up there. So then what can we do if we wanted to look at the if we wanted to look at you know, naming the components, you know, looking back at that same data dictionary, we'll see that these basically follow the same thing. So I'm just going to kind of skip past that to save a couple minutes here. If we want to look at the marker variables, I mean, you could look at it just from this, but as a reminder, what's something that you could do to make the marker variables really stand out here?
You could give it a name that's related to the marker variable question.
Well, rather, I'm talking about as far as being able to quickly assess how many marker variables are in each thing.
You use the print psych and just use the cutoff as 0.6 instead of 0.32.
Exactly. So if we just take this print psych, change our cutoff to 0.6, and then run it, you can now see that component 1 has 3 marker variables, component 4 has 3, component 3 has 4, and component 2 has 2.
So I have a question about the complex loading components. So for the complex loading components, how do you, or the complex loading variables, how do you decide which component the complex loading variables, sorry, the variables, how do you decide which component they belong to? So you have, those 4 that overlap, but like, oh, okay, never mind. Anna says we'll talk about that in a second.
I mean, I can chime in now if you'd like. Do you guys remember what we said in the end? We can't evaluate the quality of a principal component or a factor analysis with like a p-value. There's no such thing. That instead we had to do these other things to test the adequacy of a solution. And one of the things that we said we wanted to test for was the simplicity of a solution. So what does a simple structure or simple solution look like?
Is that where like only one, each variable only loads on one component?
Yes, I see it in the chat, and Casey, you said it. We want hopefully every variable to ideally find a home. We don't want outlier variables. And we also don't want complexly loaded variables. So people deal with complexly loaded variables in a couple of ways. If the difference, the delta in the loadings between one loading and another, so let's take SC103 as an example. Well, actually, let's take SC107 as an example. In the code, we have 107 loads almost 0.6 on the first component, 0.58, and it loads 0.33 on the fourth component. And so the difference between those is almost 0.3. It's about 0.3. And so if that was the case, we might force it to just load on component 1. If instead it was more like SC103, which loads 0.42 on the first component and 0.45 on the fourth component, that's probably a variable we're going to want to end up deleting because it's just really doesn't know where it belongs. It doesn't belong more strongly with one or another. So a lot of times what we'll do in that case is delete out complexly loaded variables.
Just give me 1 second. Because sorry, I just realized that we had skipped part of one of the problems, and I'm just trying to go back and find it.
So a couple of follow-up questions that I'm putting in the chat. So someone asked if there's a specific cutoff for trying to make the decision about when to cut a variable entirely versus when to keep it, but kind of count it with a particular component. And because this is an art, that really depends. So for example, the WAIS, the Wechsler Adult Intelligence Scale, has a subtest called arithmetic, which loads both on verbal memory or verbal abilities and on working memory. And even though it loads on both verbal skills and working memory, they've kept it in there because it's a really important measure of intelligence. So it has a lot of what we would call content validity. So in that case, you might keep an item on a scale because the item is really important. Other times you might delete an item because it's really ambiguous about where it belongs and it doesn't feel like it's measuring something super unique that's not already captured by other things in your measurement.
All right, and I take that back. It's later. That's didn't skip one. Just hadn't got to it yet. So then here, when we look at the oblique and orthogonal PCAs, which one do we want to retain and why?
Is this decision kind of based on I don't know, kind of like, is it based on the eigenvalues? Like you would pick the rotation that has the higher values, like indicating that it loaded more strongly?
Well, not just stronger loadings, but also so for these two in particular, they're almost the same as far as how many are complexly loaded. There's only one additional item. If there was a big discrepancy, if one of them clearly had far fewer complexly loaded things, then that might be an indication that that's the better way to go for that more simple solution. But in this case, orthogonal, as far as the correlations between the components go, what does orthogonal give us that the oblique doesn't?
I think distinctness, like the components are not connected to each other.
Right. The orthogonal allows our components to be uncorrelated with each other, which is a good thing. Is that making sense, or do we need to explain more before we move on?
Let me tackle that one a little bit because I think it's worth keeping this in mind. Josh asked whether it was directionality. I'm not quite sure what that meant. But Josh, if you want to throw that in the chat, then I can answer that. Cameron asked about unique explained variance, and that's kind of close to dancing around it. Obviously, each component has an eigenvalue, which is the amount of variance in the x variables that that component explains. And if you have orthogonal rotation, that means the components are all entirely uncorrelated. And that also means that if you sum up their eigenvalues, they're explaining each time more variance in like literally a summative fashion. So it is kind of true that if you have orthogonal, in some ways you are enhancing the amount of unique variance you're explaining, but unique in this case doesn't mean unique to an individual variable. It means non-redundant variance that you're explaining. And we also like that because in our regressions or in other analyses we might do with components or factors, which is ultimately what we're interested in, is having these scores that we can use for other analyses. Having them be non-redundant with each other means they have more ability to incrementally add to a regression model in explaining variance in something you actually care about. So for a lot of mathematical reasons, we would like them to be orthogonal unless it distorts the real relation among the variables. If it's a distortion, then we need to keep the oblique rotation.
So is this kind of like when we talk about how the circles overlap, they're just overlapping less?
Exactly. In orthogonal rotations, they overlap not at all, which would be awesome. They might overlap a lot with something you're predicting, but they wouldn't overlap with each other, which is great. But if we have them be obliquely rotated, then they may overlap. And if they overlap quite a bit, then you have to do an oblique rotation. And you're not going to explain as much variance in something else.
All right, anything else? All right, so then for number 16, looking at the macro assessment or micro assessment of this, if we're wanting to look at our communalities table, all we're going to do here is, if you recall, just the actual object itself, PCA VMAX 4 $, has a thing called communalities. But what we're going to
hang on a second. I think number 16 says to do this based on theory.
Oh, sorry. So we're switching to 3 components here. So all we're going to do is, instead of using the 4 components that we did before, copy and paste from up here number 14. And we're going to change this to the number of factors being 3, which is that based on theory. And we'll change that to PCA Vmax 3. Run that. And then we'd be able to pull up our communalities. But I want to also add, I'm going to wrap that in sort, just so that it sorts it in order for us. And I want to go ahead and also wrap that in round, comma 3, just to round it for us. Let's see, where did I left off at number 10? I'm going to go ahead and copy and paste into the document to update that with everything we have so far up to this point. Before we get into talking about these communalities here in number 16, if we skip forward to number 17, it says to examine this new rotated matrix, and then it asks the same questions that we've done before. How many have complex loadings? How many don't load? What's the highest? How many markers? And what would you name each component? Since we've only got a few minutes left, and we'll probably soak up the rest of the time dealing with this communalities, the stuff down on number 17, this should all be stuff that you have everything that you need to be able to answer number 17. So for number 17, between now and Thursday, if y'all could all just answer number 17, shoot Anna and I an email. That way we can look over and make sure we're all on the same page. But you should be able to do this, and then when we come back on Thursday, we'll be able to pick up just right on number 18. We'll review 17, but not have to deal with it. But that said, has everybody been able to get these communalities pulled up? All right, so what variable has the highest communality?
Do we want to pause and explain what a communality is?
Oh, I guess we could refresh that.
Okay, let me do that real quick. First of all, Casey is asking for clarification, and yes, please try to run number 17 yourself, and then send us the answers to the homework questions through an email before Thursday's morning class. That way we can decide if we need to go over it all together or if we can just sort of breeze through it because you guys got it. It should all be repetition at this point, and that way we can just keep moving forward with the assignment. So a reminder, a communality is the amount of variance in the X variable that is shared with the extracted components. Okay, so it's like, obviously in a PCA, we throw in 100% into the analysis, but we don't get 100% of the variance back from the extracted components. So in this part, we're asking ourselves again, okay, how much variance from the original 100% that I threw into the analysis did I get back? And Noah and Morgan have piped in with the answer.
Sorry, I was muted there. Yep, so as Noah, is it Noah? Yep, as Noah pointed out there, our highest communality is DEF 104 at 0.683. Our lowest communality is what? See a bunch of discrim 104s popping up there. And how do these compare with the communalities that we ran before? So if we come back up, where did we run this before? Did we? Oh, I'm just missing that code. So which?
Number 8, Austin. That's where I found mine.
Okay. Come up with another script. Make sure we're doing the right one. PCA OB4, is that the one we're running on? All right, so here we have the new one here on top and our old one down here on bottom. So what would you say about how these sets of communalities compare between the Verimax and the on top here and the old Opleman down here on the bottom?
It seems like the old one in a lot of cases explained more or got more variance back.
So I'm going to pipe in here. That's you guys are hitting on the right answer, but maybe for the wrong reason. We are definitely getting more variance back in the first one we did, which is the one that shows up on the bottom of the screen. But it's not because of the kind of rotation we did. It has everything to do with how many components we extracted. So in the one on top, the one we just did, where discrim 104 is 0.09 for its communality, we only took out from the 19 variables we put in, we only extracted 3 components. So of course we lost information. In the second one, the one that was actually the first one we did, where the discrim 102 is 0.27, or sorry, discrim 104 is 0.290, we extracted 4 components. And for that reason, the amount of variance we got back is larger. And as I was just saying in the chat, if we had gone all the way out and extracted up to 19 components, we would have gotten back 100% for all the variables. So the more things you extract, the more components you keep, the more variance you're going to explain, the higher the communalities are going to be.
And then just to drive that point home here, these now I've run 3. And the second 2 was the 4-factor Opleman. The third one is the 4-factor Verimax. And when you look at the communalities, you'll see that the communalities are the same because, as she was saying, that's about the number of components or factors, not the rotation itself.
And we've hit our 9:15 mark. And so we're gonna stop for today. But thank you, Austin, as always, for leading us through this, and everyone for participating through chat and voice. And send us your assignment 17 answers so that we can pick up from here next time.